My name is Olivia Piacentini. It is June 21st, 2024. Through reviewing the provided data, it is important to first organize the phenotypes into their respective classes. There are three classes they will be organized into: parental non-crossover group, double crossover group, and single crossover group. First, the parental non-crossover group can be identified, as this group will have the greatest number of occurrences. The two phenotypes with the highest observed numbers were +++ and ABC. These two observed numbers are close to each other. The next group to be identified is the double crossover group. This group will have the fewest number of occurrences. The two phenotypes with the lowest observed numbers were A++ and +BC. These two observed numbers are close to each other. The final group to be identified are the single crossover groups. There will be two single crossover groups. Single crossover group 1 will be +B+ and A+C, and have observed numbers close to each other. Single crossover group 2 will be ++C and a B+, and they will also have observed numbers close to one another. From determining all the recombinant and double recombinant classes, we can now determine correct gene placement. There are three possible gene arrangements, and these are ABC, ACB, and BAC. To figure out which arrangement is correct, we must compare it against the double crossover group phenotype A++. Between the three possible arrangements, we must ask ourselves, which possibility will produce A++? Possibility 1 will produce +B+, and possibility 2 produces +C+. Neither match our intended phenotype of A++. However, possibility 3 will produce 2+ and 1A, which does match our intended phenotype of A++. This reveals that the correct gene placement is BAC. From this, we can correct the phenotypes with the correct gene order. Now, we can calculate the gene distance. Gene distance is first calculated by adding the total observed numbers in the non-crossing over group, double crossing over group, and single crossing over group, then dividing by the total observed number of 5,742. Through calculating these values, we can find the gene distance. The distance between B and A is 18.5 map units, which is the sum of the calculated percent on the last slide for single crossing over group 1, which was 14.28 map units, and for the double crossing over group, which was 4.18 map units. The distance between A and C is 38.7 map units, which is the sum of the calculated percent on the last slide from the single crossing over group 2, which was 34.48 map units, and the double crossing over group, which was 4.18 map units. The sum of the distance from B to A and A to C is equal to 57.2 map units and is the distance from B to C. Next, the coefficient of coincidence, which is the ratio of observed double crossovers divided by the expected double crossovers, can be calculated. The double crossover expected is 0.0716 and is calculated by multiplying the distance between B and A, 0.185, and A and C, 0.387. The observed double crossovers was previously calculated when determining gene distance to be 0.0418. The coefficient of coincidence is equal to 0.584 from the observed double crossovers, 0.0418, divided by the expected double crossovers, 0.0716. Finally, the coefficient of coincidence can be used to calculate interference. Interference is the chance that a crossover event between two genes will interfere with the crossover event between two other nearby genes. It is equal to 1 minus the coefficient of coincidence. In this example, interference will equal 0.416.